Okay, we're going to continue. Now, we have said a lot about bending moment and shear force. That takes us to the next topic, which is in this subchapter, which is about what happened with the shear force. Okay. So, in the case of shear force, they will generate, of course, shear stresses, right? So, as I tried to summarize here, and I emphasized with the example that I just presented, we have to worry about L/4 or 3/4 of the length of the ship. Okay. Also, in deep girders, you will see that there is some mention of this problem also. Okay. For example, in deep girders, they ask you to have a certain area, okay, minimum area of the web. And if you analyze this formula, we'll do that in a couple of weeks. We see that that's basically what they're saying is that they're considering the shear stress on the web. Okay, so that's that. Now let's review these two equations that we have from previous from chapter 2. Okay, so do you remember what is little q here? Mr. Ortega, do you remember what is little q?
The shear flow.
Shear flow, yes, shear flow. And what is large Q? What is large Q? Large Q.
The first moment.
Mr. Chin, what is large Q? What is large Q, Mr. Chin? What is large Q? Mr. Chin, help me. No? It's the first moment, right? The sector. So we said, okay, we're going to start here, and we go up to a certain point where we know the shear stress is null. And what we can do is we can express that as the product of the area of the sector times the position of its centroid. Okay, so this is area of the sector times the position of the centroid of this sector, right? So this is inertia, this is the shear force, and this is the thickness. T of S is the thickness with the general changes, okay? So these are the expressions that we employed in case of chapter 2. Now, in the case of simple sections, I'm going to just pass by. This example is in your class notes. You have to review them. For example, this is a simply supported beam with a concentrated force. And you see that we saw here, okay? About here and about here, we have the largest shear force. And we have to worry about shear stresses in those two areas, okay? For example, you can assume that you can assume. You can analyze and deduce that because this has a symmetric plane, it's a symmetry plane, okay? We need these stresses to eliminate these stresses. They have to cancel, right? Because there is no shear force in this direction. So that means that in here, okay, tau has to be 0. Similarly as here, tau has to be 0. Now, we can apply this formulation the area and the position of the centroid along this, the flange or the deck, if you want. And then we can deduce that it is the distance from here to here is constant. So the only parameter that changes is the length of the sector. So that's why this increment is linear. And here, okay, we have two changes. First, the position and also the area. So in this case, the variation is quadratic, okay? The maximum, we expect it at the neutral axis, okay? That's something that we have to emphasize. There, okay? And another thing which is very interesting is that we could estimate the average, okay, using the vertical elements, the webs, right? So we could divide, just to have a reference value, we could divide the shear force by the vertical area or the area of the vertical elements of the webs. That's a good value, people, believe me. Okay, for example, when you have to calculate this for a hull, you have a very complex section. Okay, take the sides, take 1 or 2 longitudinal bulkheads, calculate this area, and divide it by the shear force. That's your average shear stress. And the maximum, you expect it to be a little bit above that. So that's a good parameter for you to check your results. Now, what happens when we have longitudinal bulkheads? The problem is that in that case, there is no point where we know that the shear stress is null. That's the problem. For example, this case. Okay. We do not know in this cell and in this cell, we do not know where the shear stress is null. You can say, okay, here I have a symmetry plane. Yeah, it is a symmetry plane indeed. But the problem is that you do a cut like this, perpendicular to the thickness. You do a cut here, that's not on the symmetry. Similarly here. If you do a cut like this, vertical, you will consider the full depth of the hull. So the variation of shear stress is going to be tremendous. Now, forget it. So in this case, you cannot say that the shear stress on this element is 0. So probably we'll see that about here, the shear stress is null. But specifically where, we don't know. That's the problem. So we say that this is similarly to the statically indeterminate problem. That means that only using the equilibrium equations, that's the equation that you see here. Remember, you have the axial equilibrium. It's not enough. We need something extra. And that's what we're going to include. Okay? Now, before we go on, consider this case. In this case, yes, we could analyze it completely. Yeah, for example, we could say, okay, from here, this is a shear flow. Here, this is shear flow. Here. Go on. In this direction, the shear flow will go like this. The shear flow will go like that. In here, I have the summation of these two. So it's going to be like, and then we will have like that in this. We can do something similar for the other side. So we could solve this problem completely. sure you are able to solve this problem, people. What's the difference between these two? Well, the difference is obvious, right? In here, in this holes, we know that at the cut, since it's open, the shear stress is null. And from that point, we can go on and do the calculations. So we're going to take advantage of this detail in order to implement a procedure in order to calculate this. And that's what you have to do in your homework. Okay. Now, so let's suppose we have something like this. Okay. Now, this is what we need. I think we deduced this relation at the end of chapter 2, specifically because I was thinking on using this in this chapter. Okay, gamma is equal to du ds dw dx. If we say that this is small, so this would be the slope. If we see the ship hull, okay, longitudinally, forward end, aft end, midship here, it will deform, okay? And that deformation, that deflection is W. So dW dx would be the slope, okay? When the ship hull deforms like that. This is slope. But in general, we don't expect that to be that large. So in general, this is very small. So we say this is approximately equal to du ds, and gamma is equal to 1 over g times, this is the shear stress. Okay, so this is the shear stress. So this is tau xs. And that's the formula that we just reviewed a couple of seconds ago. Now, if we integrate, okay, we integrate this. So we could start at a certain point, 0, and then integrate until another point located at position L, and the result is just the integral of this expression. So we could start, for example, in any point, for example, here, this is S, and I could integrate up to here, and this is L. And the result will give you, okay, this point here. Remember that, let me draw in a 3D, something like this. Okay, so this is a ship hull. This. So this is the x direction. In the vertical, I have, oh shoot. The z and y will be in this direction. X, y, z. Okay, so u is the deflection in this direction. So probably this will come up to here. Finally, there. So this point here moves in the x direction, this amount with respect to this point. That's what we're calculating. And for this, we need to calculate where the shear force is for the whole section. The G is a constant material. The inertia is again for the whole section. And what we need to integrate is Q divided by V. So we have to develop the first moment in this area, we have to compute the thickness. We have to integrate this, the quotient of this two parameter from here until here. Now, what happens if I integrate this, continue the integration to here? The result is that this is a closed, right? You have something like this. So I start here, go in this way, and when I return to this point, see this point has to move the same. Otherwise, it will be like that. And that means that the section will be broken, but it's closed. That means that the closed integration has to be equal to 0. So that's what we're saying here. We say 1 over g, and this is tau, has to be equal to 0. That means that u at L is equal to u at 0. In order to avoid the section to be broken out. Okay? So we're going to use that. So what we can do is we can replace this, okay, into here, and this is what we're going to do. Okay? We're going to take advantage of this. And this is basically a kinematic relation because we're talking about displacements. Okay? So the combination of one equation from equilibrium and this kinematic relation will allow us to analyze these indeterminate cases. Okay? Now, what happens in this case? Okay? What happens in this case? Yeah, we can do the same. We can do the same. We can start here and we can integrate. Jesus. People, please do not draw in here because it confuses me. You can start here. You can integrate up to here. Now, you see that these two values are not necessarily the same. Why? Because they're open. The section is open. So you can have something like this, but it's open. So you can expect the two ends to move a different amount. Maybe in the same direction, maybe the opposite direction, whatever, but could be different, in general different. Okay, so, but in this case, we could completely develop this calculation. In this case, we cannot, because in this case, we cannot calculate Q. Because we do not know at what section we can start, assuming that in that cut, in that section, the shear stress is null. In this case, yes, we can develop completely the solution. So what people have done is this, okay? They have taken this section with closed cells, okay? Closed cells. And you have something like this and put a longitudinal bulkhead, that's the result, right? You have one cell here and another cell on the other side, okay? So you have this section with cells. In this case, I'm going to explain it with 2, but in your homework, you have 4 cells, right? And you can imagine you have many cells in the section, okay? And what we can do is we can try to convert this problem originally to this one here. So if I have a cell or a section with 2 cells, how do I convert this into here? Making 2 cuts. And we know that these cuts are artificial. But we know that if we include these cuts, we could solve this problem completely, as we have explained here. Okay? So let's suppose we have this section. So we're going to do these 2 artificial cuts. These are artificial . What's wrong with this? But we know that we could solve completely for Q1 and Q2 star. So Q1 and Q2 are known. Okay, so I insist. That's why I presented the previous slide. So if you have this section with these 2 openings, 2 hatches, you could solve it. That's this case. But these 2 cuts, we have to accept that they are artificial. But anyway, let's accept. you should be able to calculate Q1 star and Q2 star completely. Okay, completely. Okay, now what's next? If you do the integration, okay, here you could calculate U. So you could start here. You can say, okay, I'm going to calculate U0 and I'm going to integrate all the way up to here. What's going to happen? That in general, UL and U0 are not the same. So it's like having something like that. Yeah, it's natural. Why? Because we have included a cut. But we recognize that our original section does not have a cut. So we have to include something extra in order to make it believe that in really, this is not like this has to be like this. See, right now, we make a cut and the result is this. So we have to make a correction in order to put this back in place. And that's what we do next. So we apply Q1 and Q2 in each section. What we're going to be, to simplify this process, is that Q1 and Q2 are constant. So let's put it here. Q1 and Q2 are unknown shear loads. Are constants. Okay. So we have to superimpose these two, Q1 and Q2. Q1 in cell 1 and Q2 in cell 2. People, it's very important that we keep track of the sign. We assume Q1 and Q2 are positive, so we put it in the counterclockwise direction. Okay. And now, how can we find Q1 and Q2? Well, we know that right now, because of the cut, the two ends here are like this. So we have to include Q1 so that this go back, Q1 and Q2, this go back to this. And similarly, in the second cell, right now, because of the cut, we have something like this. We're including Q1 and Q2 so that we go back to this. So for cell 1, okay, we said that if we integrate in the cut, from the cut until back in the cut, the two axial displacement has to be equal between them. So that's one equation. And that equation includes Q1 and Q2. And the other equation will be, we have to do the same for the second cell. So we start at the cut, we integrate all along the cell, and at the other end, the result has to be equal to the first at the beginning. And for that equation, we are going to consider Q1 and Q2. So we have two equations for two unknowns, which are Q1 and Q2. And from that, we should be able to find the solution. So the rest is just algebra. We have to be careful with the signs. That's very important, but that's all. Now, so we have Q star and QI. Okay? And divided by B, that's in general. Okay? That's the shear stress. And yeah, this has to be divided by G, but we put here G times 0. And G times 0 is 0. And G is a constant, positive, so there's no problem, okay? So, yeah. Let's erase that. Damn it. People, are you with me so far? People, are you with me?
Yes, doctor.
Okay. Now, what we do is this Q star is known because the left-hand side, we know that we could solve it completely. So Q star 1 and 2 are completely known. So we can put them on the right-hand side because it's the independent term. Oh. And here, Q star is equal to V over I sub C, but that is constant. So we can take them outside. And the rest is here. I put it on the right-hand side, that's why I have the negative sign here. On the left-hand side, the integration of this, since we assume that they are constant in each cell, Q1 is constant, Q2 is constant, we can take them outside the integration. And this integration is very simple. Because if we want to integrate, for example, from here, let's integrate, no, here, let's integrate this. From here, we go like this, like this, like this, and like that, right? In here, the thickness is probably constant. Deck has a certain value for the thickness. So the result of this integral will be the length. So this, in this case, will be half of the beam divided by the thickness. Then we integrate plus the side. On the side would be the depth times the thickness of the side. We go to the bottom, we go to the bulkhead. So this integration is very simple. This integration gives us some problem because this could be linear and in some cases could be quadratic. Right? Remember, it's linear and the deck is quadratic on the side. So you have to integrate that, yeah, but it's just linear integration, quadratic integration is not very complex. Okay? And these are the unknowns. So, okay, these are unknowns. So this is a linear system of equation that we have to solve to find Q1 and Q2. And once you have Q1 and Q2, you have Q star, this is known, plus Q1, 2, and that's the total flow. And you can divide it by the thickness, and you can have the shear stress distribution in each cell. People? Okay, for example, this example is in your briefly described in your class notes. Okay. For example, let's do this integration. We start here, go like this, like this, like this, and like that. The problem is here. Why? Because if I go downwards, this is the direction of the integration, you see that Q1 points positive, right? So this is positive. But the Q2 goes in the opposite direction. So for the integration along the longitudinal bulkhead, we have to consider Q1 positive from here to here, and then we have to subtract because Q2 is going upward. That's why I'm using the negative sign here. But only in the longitudinal bulkhead. Okay. Similarly, when I do the integration in the second cell, Q2 will be positive. But along this, Q2 goes up, but QU comes down. So in that case, I will need a negative sign for that. So we have Q1, we got 10, 10, 10. So this is 10. This is 10 meters. This is 10 meters, and this is 10 meters. So we go 10, 10, 10, and 10. In this case, is 1 centimeter is constant over the whole section. We should do something different. And minus 10 over 10 of 1, which would be this integration for Q2. And this is the integration in here.
Doctor, but here we have two Q stars at cell 1 and at cell 2.
Yeah, because see, you can calculate the Q star in this cell, and then you have a different Q star in this cell. Q star here is like this, like this, like this. Here. Also, you start at 0, and you start going like this, whatever. So we know, but in the other side is something like this. So this distribution is what I call Q1 star. This another distribution is Q star, Q2 star. Santos?
Okay.
So it's just Q1 is the shear flow in cell 1. Q2 star is the shear flow in the second cell. In your case, you're going to have 4 shear flows. But don't worry, I'm going to help you with the computer program. I give you the computer program. I just say, okay, this is the data, and this is the result that you can expect. Yeah, this is a black box. We have to be very careful with black boxes. That's why I'm trying to explain a little bit more so you can use efficiently this program. Okay. So we have something similar for Q2 there. Okay. And then we have to solve this problem. So we have Q1 and Q2. Q1 star, Q2 star, I'll already know. So we can proceed and calculate. Okay, now this procedure that I'm explaining here is the one that you have to use, but using a computer program. And I'm going to explain that tomorrow, since it's a practical session. Okay, tomorrow it's Friday. Oh man, tomorrow there's no class. Okay, so what I'm going to do is I'm going to do a video because I have to recuperate. Or should we have classes, people? Should we have 1 hour of class? What do you prefer? That I give you a video or I can explain in a regular class? What do you prefer? Video? Well, talk to me.
In my opinion, I would like the video, but I don't know what my partners want.
Okay, I'll try tonight to do the video, and I post it so you can know how to use the program. It explained already in the class notes, but just in case, okay? And that's it. Yeah, that's about half an hour, and that's all. Okay, before we break, I wanted you to be, okay. This is, okay, can you see the PDF?
Yes, doctor.
Ah, no, that's not. What is this? Somebody. This is individual work, right? So How many people do we have right now? Okay, would you please, Ms. Valdez, would you please start help me with the reading this problem one?
Yes, doctor. The first, for the box barge analyzed in class 100 times 18 times 9 meters, integrate load distribution to calculate the shear force and bending moment distribution on the ship hull in the still water and then in waves in sagging condition. Present
Okay,
results.
so just a second. So what I show you here is one, I think it was a hogging condition. So what you have to do is you have to do the same, but in the sagging condition. Okay. There are several ways to do it. Since the weight distribution is simple, it's just in the aft part, then you have the holds that has empty space, and you have the forward. You can even integrate analytically. Okay, you integrate from -L/2 until here, evaluate the result here, then you, with that result, you start integrating from here to there, and so on. So you could do this integration analytically if you want, or you can do numerically in the way I explained today. Both ways can be done. This can be applied for this assignment. Okay, so you have the weight distribution. For the loading, for the buoyancy, you have to calculate mean draft and trim angle. And from that point, you can go on and do the integrations. At least try to use 20 intervals, right? Because otherwise, as Ms. Santos pointed out, the curve for the bending moment is not going to close. Okay, now, if you use make some errors in the integration, yeah, the curve is not going to close either, shear force or bending moment. So what you have to do is, that's your check. If the curve closes, that means that your calculations are correct. If not, you have to review it. And in that process, we learned a lot, believe me. Please continue.
Present results with sign conventions of the ship classification societies for the numerical integrations employed at least 20 intervals and identify points where extreme values occur.
Yeah, so two things. First, you have to use the sign convention of the classification society rules. Yeah, we have to follow. If somebody asks you to do what do we call the loading manual for a tanker, right? You have to present distribution of shear forces, bending moments, and different loading conditions, this and that. Yeah, and for all of that, you have to use the sign convention. So from now, you have to start preparing yourself for that. At least 20 intervals. If you use less than that, probably the curves are not going to close. So if you want to use more than that, yeah, that's fine. But at least 20. Okay, let's see somebody else. Mr. Llanos, would you please read problem 2? So for problem 1, you have everything. You should start right now.
Good morning, doctor. Yes, the second problem says that apply DNB formulations for ships with length greater than 100 meters to approximate bending moment distribution in still water and in waves. Graphically compare.
So just a second. So please, I want you to start familiarizing with the application of classification rules. Okay, so we have had some exercises where you have to apply the rules. Yeah, that's what we want to do. So you have to review that. In what section? I don't know. Look it up. Longitudinal strength. Okay, there is a section on longitudinal strength. I think it's section 5. And you start seeing all the details. There is a section for still water. There is a section for moment. And then they will describe the distribution, the shape that I just showed this morning. Okay, so it's constant in here, and then some variation closely to linear up to the forward and aft ends. Okay, so you have to calculate that, and then you have to see the distribution, then you simple to draw. Okay, go on.
Graphically compare with results from example developed in class and with results from problem 1.
So you are asked to do something similar with the example that I presented this morning for the 42-meter long patrol boat. So you plot the distribution of bending moment in a simplified way, and then the distribution of the bending moment using the equivalent or equivalent wave in a quasi-static equilibrium. Okay. Remember, this is not a real ship. This is a box barge. So in general, I don't expect to be 3-to-1 or 2-to-1. But in general, you have to expect that the distributions, the weight distribution that we're applying is simplified, and the lines, the ship lines, are different from the lines that of a real ship. So we should expect differences, okay? Because we're applying the rules as it were a real ship, and it's not. So be flexible in your mind, okay? So 2 problems should be done over the weekend if you have some time. In problem 3, it's let's see, somebody else. Miss Aviles, will you please read problem 3?
Yes, doctor, good morning. You are to assume in a conservative approach that the sectional inertia of a ship may be approximated considering only the shear plating.
Just a second.
Select the
Just a second. So you have the section, right? The section that you see here. But I don't see longitudinals. And the longitudinals also contribute to the sectional inertia. So we are going to, in a very simple way, we're going to consider only plating. I know when we include the longitudinals, that will increase the inertia. But we're going to take that as it were a safety factor, okay? If we are okay right now, if we include the longitudinals, that will increase our safety factor. So we are being pessimistic in certain way, okay? That's what we mean by that. Go on.
select the thicknesses for the different parts of the section: bottom, double bottom, sides, long, bulkhead, and deck, such that they satisfy DNB requirements for minimum midship section modulus, section 5, C 304, and bottom
So
and
they
bottom.
will give you in that rule, section 5, C 304. Okay, that will specify the minimum. Okay, so you have to satisfy that. So what you have to do is you have set up a table with these elements, and you have to play around with the thicknesses. Okay, go on.
At bottom and double bottom thicknesses must be layered. To
Arjun.
select thicknesses
So this is typical. When you see the midship section of a ship, usually the thickness at the bottom, you see that this is larger than at the sides or at the deck. It's typical. Okay, so let's try to get ready to work as professionals. Okay, go on.
to select thicknesses of the elements, you have to find the available values for ASTM and 131 grade A steel and include the consorted tables.
So this is the material that we are going to considering. Okay, I asked somebody who is a practicing engineer, and he said to me that that's the typical material that they're using right now for naval construction. And finally, at the end, Ms. Aviles, at the end, there is a comment.
Find in the web a similar ship structure and compare her thicknesses with your results.
Okay, so let's see if you can find a ship structure of a ship with these dimensions, okay, beam and depth. And man, there is no, the depth is not there. I'll have to review that. Okay, but the idea is that you see the thicknesses that you have chosen, you have to compare them with the thicknesses in a real ship. So it's a matter of seeing if your results make some sense or not. So you have 3 problems that you can completely done by next week. Okay, and the last one, yes, I will prepare a video on how to use this program, and I will post it so you can follow, and that's it. Okay, people, have a nice weekend, and please start the homework. And remember the recommendations that the two students shared with you, right? Okay, they did pretty well. I'm really happy. Congratulations again, Mr. Pesantes and Mr. Gomez. You did pretty well in the evaluation. I'm really happy for you, and I'm really happy for me because every time I give a quiz and people do well, that means that I'm in a way I'm responsible for that too. So yeah, I'm really happy. Okay, have a nice weekend. Bye now. You can stop the recording, Andy.